Welcome to this video here where we're going to solve a tangents, normals, arc length, and curvature question from the practice problems we did. This is question 7 here near the end. It's a curvature question tacked on with some other things. And what I want to actually do with this is I want to talk problem solving strategy because this is going to all be techniques that you know how to do at this point, but you got to chain them together in a particular way. And so what are we trying to do here? We are trying to find the curvature of y equals e to the alpha x at x equals 0. Now, notice we don't know what alpha is. But that's fine. We can just treat it as a constant and still differentiate just fine. That shouldn't affect things. But then this problem takes a big shift. We want to make the curvature as large as possible. And all of a sudden, that means that this yellow part that I highlighted is actually a max-min problem. And it'll be a Calc 1 problem, a max-min problem with alpha as the variable. How do I know alpha is going to be the variable at that point? Well, because what we're going to do is we're going to find kappa. We're going to find the curvature, which will be a function of x, but there will also be alphas around. And then we're going to plug in x equals 0. And so we're going to have a formula for kappa that depends on alpha. And we'll do standard max-min stuff. Now let's see if we can actually put that together. First, I want to point out that we've got y equals e to the alpha x. This is just a standard single variable calculus function. That means we get to use this formula for curvature. You could use a variety of other ones as well, but we're going to jump into what we've got here. Y prime squared to the 3 halves. This is the formula that we're going to use. We have a bunch of other formulas, but this one is really great for single variable type functions. Now you'll notice that I need y prime out of this. That is a chain rule derivative or a generalized exponential rule. We need y double prime, which is alpha squared e to the alpha x. And then I actually am going to plug in, I'm going to create myself a little column here, and I'm going to plug in x equals 0. Because at this point we've taken the derivatives, we can plug in x equals 0. Y is 1, y prime is alpha, y double prime is alpha squared because e to the 0 is 1. And that now lets us compute kappa. Kappa is the absolute value of y double prime. That's alpha squared. It's already positive. Over 1 plus alpha squared. That's y prime squared to the 3 halves. That's a formula for our curvature. Now, you can start just imagining which curvatures you're going to use. First of all, like curvature or which alphas you're going to use. When alpha equals 0, this function is actually just y equals 1, which is a constant straight line, should have no curvature. A straight line doesn't curve, and that's what you get in the formula. When alpha equals 0, you're getting 0. Another thing I notice is that when alpha is positive, like say positive 2 or negative 2, you're going to get the same answer because you're always squaring alpha. But we want to find the maximum of kappa. We want to figure out which alpha, treating alpha now as an input, is going to maximize kappa. And that means we just go back to single variable calculus again, and you want to find kappa prime, the derivative of kappa with respect to alpha, in order to make this work out. Now, what is this derivative going to be? It's a little bit of a complicated derivative. Let's work it out. The derivative of the numerator times the denominator, 1 plus alpha squared to the 3 halves, minus the numerator, alpha squared, times the derivative of the denominator, and I'm running off the edge of the screen, but I need to do a chain rule times 2 alpha. So you should double check that derivative, that in particular, starting with the 3 halves, that is the derivative of the denominator. I need to put it over the denominator squared, 1 plus alpha squared to the 3 halves squared, just cancels out the half exponent. This is k prime, and we know when we're trying to find maximums or minimums, take the derivative, set the derivative equal to 0. Find those critical points here. So this is going to be 0 equals, well, if I'm trying to figure out when this whole fraction is 0, I can focus just on the numerator. And so I'll say this is 2 alpha, 1 plus alpha squared to the 3 halves minus alpha squared times 3 halves, 1 plus alpha squared to the 1 half, 2 alpha. That's what we need to solve. And now we can sort of abandon this whole slide because we don't need the problem anymore. We just need to say, hey, let's find the critical numbers. So let's come to this next slide and do that. Bunch of ways that you can go about it from here. Technically, probably the most technically accurate way is to factor out a GCF here. For sure, we should cancel a couple of 2's out of this. And so you can get 2 alpha, 1 plus alpha squared to the 3 halves, minus alpha cubed, 3 alpha cubed, 1 plus alpha squared to the 1 half. And this 1 plus alpha squared to the 1 half is actually the GCF here. There's also an extra alpha you can factor out if you want. And so let's do that. We'll take out an alpha. We'll take out a 1 plus alpha squared to the 1 half because they both have that in common. It leaves behind a 2. It leaves behind a 1 plus alpha squared. It leaves behind a minus 3 alpha squared. That's all that's left behind once you drag out of both of them an alpha and just one of these alphas here, and also a 1 half of the exponent. So it's still 0 equals alpha 1 plus alpha squared to the 1 half. And in here we'll get 2 plus 2 alpha squared minus 3 alpha squared. And we'll use the zero product property, which says, hey, how you solve any equation, get it equal to 0 and factor it. This says alpha equals 0. It says 1 plus alpha squared, technically square rooted, equals 0. And then this last one, I'll do a quick simplification. 2 minus alpha squared equals 0. Well, alpha equals 0 turns out to be the min. If we go back to our kappa, everything's going to be positive except when alpha is 0. So that's a minimum. This one, no solutions. We have no critical numbers there. This one, alpha equals plus or minus square root of 2. Well, it turns out that's going to be the maximum, in large part because we can sort of see the shape that we know that this graph, if I were to graph kappa and alpha, we know we start at 0, but it's also what's the limit as you go out forever. As you get to infinity, alpha squared, exponent 2, denominator's alpha squared to the 3 halves. That's an alpha cubed. The denominator wins. Our graph has to look like this, and it's symmetric. So there has to be a maximum. That maximum happens at root 2. E to the root 2x is what's giving us our maximum curvature at 0 here. That's it for this video. At its core, for us in multivariable calculus, it's really just a curvature calculation, just so we can see how it happens. But also pointing out that now you can start doing things with this to figure out how are we going to make this thing curve the most. I guess the curve. This is just a graph of kappa, but how are you making e to the alpha x curve as much as you can? And there we go. That's it for this video. I'll see you in the next one.